Hi, my name is Konstantin Rябинин. I am from Perm State University, and on behalf of my colleagues Roman Chumakov, Konstantin Belousov and Maria Kolesnik, it's my pleasure to deliver an invited talk about the Ontology-Driven visual analytics platform for semantic data mining and fuzzy classification. Digital activities of humans and software systems all over the digital earth result in big data, traditionally characterized by volume, velocity, and variety. The main driver of big data processing technologies is variety, because it requires smart solutions based on artificial intelligence to be involved. But one another essential V is visualization, bridging the gap between big data and human experts. Variety is efficiently tackled by ontology engineering methods. Ontology is a formal model of application domain that consists of thesaurus of application domain concepts, set of relations between these concepts, and set of axioms. Ontologies can be used to bridge semantic gaps between the data applications, data mining algorithms, and data mining results, and provide a formal way for representing the data mining flow. This is called semantic data mining, and it is elaborated in a plethora of works, for example, in the works listed in the slide here. These works prove that ontology engineering is an efficient way to tackle the big data issues, for example, variety, velocity, and volume. But the next question is, if visualization can be tackled by ontology engineering as well? Our answer is yes, it can. To prove this, we provide a software solution called Skizzy. It is a semantic data mining platform, and roughly speaking, it is a sum of control modules plus sum of operators. Each operator is responsible for data loading, data transformation, data visualization, and so forth. Operator consists of implementation and its ontological description. The implementation is actually a microservice that can be written on our own, or some third-party library can be taken. For the description, so-called lightweight ontologies are used. This means that the set of axioms is empty. The set of relations contains only 8 types of relations, which makes the reasoner pretty straightforward and simple. Actually, the axioms are incorporated into the code of the reasoner, so there is no need to store them in the ontologies. The thesaurus contains such concepts as operator, type, input, output, worker, computing resource, and so forth to efficiently describe each operator. Using these ontologies, Skizzy automates the chaining of the operators and maintains their interoperability, so the user can transparently build the pipelines to solve particular data mining tasks, starting from the input data up to the visualization and interpretation of results. The Skizzy workflow is as follows. Skizzy knowledge base contains ontologies describing all the available operators which are joined into sets according to the task classes to be solved. The user chooses a task class, and ontology merger automatically builds a joint domain ontology that describes all the operators suitable for this task class. This domain ontology drives the graphical user interface generator and operators linker, which provide a palette of operators. The user builds a so-called data flow diagram, specifying the desired data mining pipeline of operators. Skizzy automatically converts this data flow diagram to the set of task ontologies, which describe particular pieces of work distributed over the different computing resources available in the Skizzy network. For each task ontology, the corresponding executor is spawned on the suitable computing resource. The execution results in interactive visualization, or some other artifacts are generated. For example, the firmware for the electronic devices within the Internet of Things. However, the cases beyond the visualization and visual analytics lay outside of the current talk. Skizzy is an open source project freely available in the web. The link is on the slide below. The changes of the knowledge base change the entire behavior of the platform. So we can introduce new features just by appending new knowledge to the knowledge base, without touching the source code of the platform's core. Let's see how SciVi is used to solve real-world data mining tasks. The first one relates to the fuzzy classification of mental maps within the digital humanities application domain. A mental map is a generalized spatial experience in humans' mind. In our experiments, we ask informants to draw their mental maps using the Creative Map Studio vector graphics editor. In this way, we get digital representations of regional mental maps, which are then analyzed in SciVi to reveal the knowledge about the state of regions. For example, the input data are different digital representations of mental maps of the Russian Federation. This is a real map of Russia, and these are the possible representations drawn by different informants. Each representation is a vector image encoded in a JSON file. We built this kind of data processing pipeline in SciVi to load the maps drawn by informants from known regions and some maps from unknown informants. Then we use patched version of the weighted fuzzy pattern matching algorithm to classify the unknown maps. Each operator denoted here as a box has its own ontological description. For example, this is the ontology of WFPM operator. It states that WFPM stands for weighted fuzzy pattern matching, is a fuzzy classification operator. It has a lot of settings, for example, X weight, Y weight, size weight, and so forth. It has two inputs, pattern maps and test maps, and you can see these two sockets on the data flow diagram, which correspond to the inputs. And one output called weights, it's a grid and it's denoted here as an output socket. Also, this ontology describes the implementation of this operator. The implementation is called WFPM worker. It is suited for the server side, it's written in Python and located under lib/fuzzy/WFPM-py. From this ontology, SciVi knows how to build this graphical user element and how to execute the corresponding operator. The detailed description of WFPM operator with all the formulas can be found in the SciVi repository. The link is on the slide. It must be noted that this data flow diagram mixes operators for the server side and for the client side. SciVi automatically builds a task ontology from this data flow diagram. Let's see its fragment. This fragment includes just two operators. You can see here the WFPM that is hosted on the SciVi server and the subsequent operator slider that is hosted on the SciVi client. This link here, called isUsed, corresponds to this link on the data flow diagram. As the chained operators are hosted on the different computing resources, SciVi knows that this task ontology should be split up into the pieces, like this. And this link is automatically supplemented by the data serialization, marshalling, and deserialization operators. So the data flow is completely transparent for the user. The user just connects these two operators without bothering on which side theirs should be executed. And SciVi takes all the work related to the data transformation and data transfer. Let's see how it works live. Here is our data flow diagram loaded in SciVi. Let's start the visualization. And we can see the world map and the slider down below. Oh, I think my video overlaps the slider. I can fix it very quickly. You can see that the operator that corresponds to the slider is below the operator of the map. Let's shift it to the top, start the visualization again, and SciVi regenerates the entire graphical user interface, so the slider is on the top. Now, when everything is visible, let's move to the map. The regions marked here correspond to the patterns. That means we get the informants from different regions, for example from Perm Krai or from Tomsk Oblast, and ask them to draw their representations of Russia. According to the maps assembled, we created the patterns, and now we can classify the maps drawn by informants with unknown residence region. For example, let's choose the unknown map with this slider. you can see that the map changes its colors. For example, this map with the code 3789122 resembles at most the maps drawn by informants from the Republic of Bashkortostan. And for example, this map resembles at most the maps drawn by informants from Perm-Krai. In this way, we can guess the residence region of the informants. It must be stressed that everything here, the entire graphical user interface, including the slider, the map, its colors, are generated just according to the data flow diagram, without any programming. The second use case is about the modeling of ontogenesis of Titanophanaeus, the extinct Permian synapsid. The application domain here is paleontology. Studying the creature's life cycle is a key to understanding their lifestyle. While we have enough data about the life cycle of the living beings, for example, of humans, we have too little data about the extinct creatures, for example, Titanophanaeus. So, in the latter case, the modeling is required. Input data here are high-precision 3D models of skulls of young and adult Titanophanaeus species. These models were created in a joint research work of the Perm State University, the Museum of Permian Antiquities, the European Center of Paleontology, the University of Opole in Poland, and the Russian Paleontological Institute. The following data flow diagram is used to process the data. Again, we have a slider here and two models which are morphed according to the slider's value. Let's see it live. Here is the pipeline loaded in SciVi, and let's start the visualization. And again, we have this problem with the slider. Let's go back and repeat the trick. Just move the slider to the top, start the visualization again, and now the slider is on top of the 3D scene. You can see the skull of the young Titanophanaeus species. And when we slide the slider from 0 to 1, it gets older, up to the oldest known species. But when we continue sliding, the interpolation between the skulls is changed by the extrapolation. And surprisingly, the result is still plausible. The skull looks very natural. And what is more interesting, it resembles another synapsid, Anteosaurus, from the same family. This resemblance is a weak evidence that the linear extrapolation is correct, and Titanophanaeus and Anteosaurus may have similar growth curves. In contrast, when we extrapolate to the other side, below the zero, the model collapses. It collapses entirely. This phenomenon indicates that the growth curve of Titanophanaeus is non-linear of the juvenile segment. Here on the slide, the results are summed up for different morphing values. As you can see, the data mining platform can be applied to solving tasks in very different application domains, and the new functions are introduced just by appending new knowledge to the knowledge base. These were just two among multiple SciVi use cases. The two practical consequences we can make are that both variety and visualization problems can be tackled by ontology engineering, and that microservice-based ontology-driven architecture is suitable for semantic data mining. Currently, SciVi platform is about to grow in four major directions: fostering the tools of advanced visual analytics, so-called VA SciVi Workbench, enabling experiments in virtual reality, VR SciVi Workbench, enabling brain-to-computer interfaces, Neuro SciVi Workbench, and supporting ontology-driven edge computing, Edge SciVi Workbench. Each workbench reuses the main principles of SciVi and brings its own array of microservices, which act as operators joined into sets covering particular task classes. This work was supported by Russian Science Foundation. Thank you for your attention.